Okay, let's go ahead and get started. Um, so in chapter 6, we're dealing with a lot of kind of new ideas, right? So at the beginning, we started talking about electromagnetic waves, electromagnetic radiation. So waves have a frequency, a wavelength, and an energy. You can also think of light as being comprised of photons. Photons have energy. And so once we go through that, we start looking at the Bohr model. And the Bohr model tells us that the energy levels of the electron in hydrogen are quantized. So they take on specific values. And then we say, you know, well, look, we look at this Bohr model, but it has certain limitations. It cannot be used to describe other elements. So we need something that's a little bit more robust in terms of the theory. And so that's where De Broglie comes in, and he figures out that in fact, not only do photons have wave particle duality, but actually electrons have wave particle duality, at least they should. And experimental evidence suggests that that's true. So what we're going to look at today is what's called quantum mechanics. We're going to look at just really one section of it, and then we'll get further along as the week progresses. Specifically, we're going to look at this idea of the Heisenberg uncertainty principle. But before we get to that, I want to give just a little intro into the idea of this quantum mechanics. And there's different terms that are used to mean the same thing. So sometimes people will use the term quantum. That was brand new, and it still doesn't work. Pull that out, right? Quantum mechanics is one way that people call this. And another term is wave mechanics. And we're going to focus on an interpretation of this that is more in line with what we would call wave mechanics. So remember, De Broglie essentially said, look, you have the nucleus of an atom, and you've got this wave, which is the electron. Okay? So it's just some sort of vibration around the nucleus. It's a standing wave, so it's not a wave that's traveling through space. It's just sort of vibrating around the nucleus. So it's a standing wave, like a musical instrument. Okay? And so this wave is the electron. And what happens is people start to ask the question, okay, well, if there's a wave around the nucleus, which is the electron, there must be some mathematical function, because essentially all waves can be modeled mathematically. And so Schrodinger is one who figures this out, and he uses the symbol psi. So this is pronounced psi, the hard I. Okay. It's a Greek letter. And this is what we call the wave function. Okay. And so if you were to take a more advanced chemistry course, a junior level course, what you would do is you would look at this wave function and do analyses of it and calculate things with it. But essentially the wave function tells us what equation describes that wave, which is the electron. And it's subject to certain physical rules. It's an electron that has mass and it has a vibration. Okay? Now it turns out, for reasons that I won't go into, that it's very, very difficult, if not impossible, to interpret some of the aspects of that function. So for example, what does it mean to say that an electron is vibrating? What does it mean to say that it has an amplitude? It doesn't really have much physical interpretation that people can figure out. However, there's a guy by the name of a physicist by the name of Max Born who figured out that if you took this wave function, I'm going to take the absolute value of it and square it. So you take this mathematical equation, you square it, right? Like 6 squared, right? If you do that, that will tell you something about probability. Okay? And probability is like the likelihood of something occurring. So for example, if I roll a die There's a probability that it'll come up as a 1 out of 6. There's a probability it'll come out as a 3, right? 3, same probability, 1 out of 6. Right? So probability is the likelihood that something will happen. And that has been used, that idea has been used to say the following. We use chi-squared to calculate the probability that an electron, or the electron, is some distance from the nucleus. Okay? The probability that the electron is a particular distance from the nucleus. Meaning, if this is the nucleus right here, what's the probability that it's this distance r? What's the probability that it's this distance or this distance? And that can be mathematically calculated, and then you can calculate the energy that it would have, and you can compare that to experiment. And so what you end up with is something kind of interesting. You end up with a graph. This is distance from the nucleus. This is the distance of the electron. So we're talking about the electron, and this is probability on the y-axis. You get something that looks like this. Looks like that. Okay. So the probability is very high when you're close to the nucleus, when the electron is close to the nucleus, and then it falls off pretty rapidly. When you get further and further away from the nucleus, the probability becomes smaller and smaller. So it's not very good, not very high probability that it's far from the nucleus. Most likely it's near the nucleus. Okay? The significant, or one aspect of this that's significant, is that we're no longer saying how far is it from the nucleus, we're saying what's the probability that it's this distance from the nucleus. And that's a different statement. Like if I say that that wall is, 5 meters from me, versus there's a 30% probability that it's 5 meters from me, those are different statements, right? So what we're claiming is that at the atomic level, we really cannot answer questions of where is the electron, but we can say there's a probability that it's this distance. Okay? And what you find is that, for the most part, the electron stays pretty close to the nucleus. So it's somewhere around here. Okay? And it's around here. So often what we do is we draw like a little fuzzy cotton ball around the nucleus to say that the electron is somewhere in this space here. We can be pretty sure that it's not over here. That's too far. That's like way over here. But it's somewhere in this range here. Now, what happens is, if you actually look at it, this curve, if you actually expand it out, it actually mathematically never reaches 0. It gets closer and closer to 0, but it never gets there. So in fact, there is some probability the electron is over here, and that has certain physical ramifications. It turns out that if I take another atom over here, another nucleus, this electron, there is some probability that this electron can be over here. And so it might actually be over here as well. So it can actually occupy spaces that you might not have predicted because this probability is not actually 0. There seems to be some physical evidence that actually is the case. Okay? So what we do is we call this little fuzzy picture that I've drawn here, we call it an orbital. Orbital. So it sounds like orbit. So it's kind of in a way saying, look, we talked about orbits with the Bohr model and the planetary model. So we're not going to call this an orbit because it's not a specifically defined orbit, but it's kind of like an orbit. So we'll call it an orbital. And it's a probability distribution. And it's the likelihood the electron is around. So if I were to do the following, it's kind of interesting. If I were to take this nucleus and put in 2 protons instead of 1, it would have more positive charge.
what you would have, which is supposed to, is this orbital would just get smaller. So it would just be closer into the nucleus, right? Because there's more positive charge, the electron's going to be more strongly attracted to it, so it'll just shrink, it'll just get smaller. So this probability distribution will just get smaller like this. A bit tighter like that, right? So it turns out these orbitals have different sizes depending on how many protons are in there, also depending on how many electrons are in the atom, and each atom is going to have its own specific orbitals, which are probability distributions. Okay? And that's what we would call wave mechanics or probability mechanics or quantum mechanics. And we'll talk more and more about a little bit about the arithmetic when we get into the next section. But I do want to talk a little bit about this one problem that is in this section here. And I think this is section 6.5. And it has to do with something called the Heisenberg uncertainty principle. So let me write it out here. Heisenberg. This is a name you maybe have heard of. The Heisenberg uncertainty principle. It's an important aspect of quantum mechanics. It's actually even goes beyond that. It's actually an important aspect of measurement in general, how we measure things. Because remember, science is based on measurement. Like we can talk all we want about the theory of chemistry, but in the end, when you go into the laboratory and you mix these chemicals together, the real proof of what we're talking about comes about in that experiment, right? So for example, today, some people did this experiment and they got a molar volume of 30 liters per mole. Other people got 20 liters per mole. That's a contradiction. People are getting different answers. So if we really wanted to solve this issue, we would do more experiments to figure out what the actual value is, right? So we only had time to do it once, but if we really wanted to know for sure, we would develop more advanced experiments and we would practice it, and then we would get good at it, and we would try to really lock down what the actual value is. Right? So the Heisenberg uncertainty principle has to do, for our purposes, it has to do with essentially the idea of measuring two things regarding the electron. And the first thing that we're trying to measure is the position of the electron, where it is. And typically, when we talk about position, the symbol that we use is X. If you've taken any physics courses, you know that when you're talking about where something is, the symbol X is very often used, right? Position X. The other thing we're trying to measure is the velocity. And we've talked about velocity. We've talked about the velocity in this course in terms of gas molecules, how fast they're moving. We've talked about the velocity in terms of kinetic energy, how fast an object is moving, 1/2 mv squared is kinetic energy, right? So velocity is something that people are often very interested in terms of particle. So what we're going to do is we're going to look at the idea. Imagine that you have an atom and there's an electron in it. So here's the nucleus, and there's an electron. And we're saying that this electron is somewhere in the space around the nucleus, right? The question is, can we do a calculation to show where it is? And can we do a calculation to show how fast it's moving? And so the Heisenberg uncertainty principle says that these two measurements are related to each other. And they're related to each other in a particular way. It's not necessarily obvious. We might expect that we could measure this and then separately measure this and know both of these values. What Heisenberg said was you cannot really do that in the way that you think you can. He says at the atomic level, the better you know this value, the worse you'll know this value. That measuring this one affects your understanding of this one in the opposite direction. Okay? Alternatively, the better you measure this one, the worse you know this particular value here. So you put all your effort into finding the position, that's fine. But when you do that, you're going to lose information about the velocity. And that's not an obvious thing. In a way, that's sort of counter to what we normally think in terms of physics. We normally think, hey, let's try to make this a rocket. We want to know how fast it's moving at all times. And we want to know where it is at all times so that we can get it into orbit. What he's saying is that at the atomic level, you can't do that. Knowing one worsens your understanding of the other. Okay, and that's called the Heisenberg uncertainty principle. There are other relations as well. There's energy and time. There's other ones as well. So what I'm going to do is I'm going to write the equation that we're going to use for this one, and it's delta x times delta p, and that has got to be greater than or equal to Planck's constant over 4 pi. Pi being the pi being the circumference of the circle divided by its diameter. Okay. So what's this p? Well, p is momentum. We talked about that earlier. And momentum is mass times velocity. Amount of motion in something happens indeed. So the uncertainty is this delta. So delta x is the uncertainty in position. We're talking about the electron. So it's the uncertainty in terms of its position, and then delta p is the uncertainty in momentum. Now, the uncertainty in the momentum is not due to the uncertainty in the mass, but the velocity. It's because we don't have perfect knowledge of the velocity, so that imperfect knowledge of the velocity shows itself as an imperfect knowledge of the momentum. So it's really this right here, it's the velocity distribution. So what I'm going to do is I'm going to substitute it here. I'm going to change it a little bit. I'm going to, just to make it easier to do the problems, times m delta v. So it's the uncertainty in the position times the mass times the uncertainty in the velocity has got to be greater than or equal to h over 4 pi. Okay, so this is just a constant. We know that value. This is just a constant, 3.1415. This is just a constant 4. The mass would be the mass of the particle that we're talking about. So typically it's the electron. And then this would be the uncertainty in the position. And this would be the uncertainty in the velocity. These three multiplied together have to be at least equal to, but can be greater than this ratio right here. Okay? So how does this play out? In terms of these problems, you see problems kind of like this. They say, look, you've got an atom of neon, and it has a radius of 38 picometers. So it's giving you the size of the atom. And we would actually, this is the radius, so the diameter would be twice as big. It has an average speed, so the atom is moving in the gas phase at 350 meters per second. Okay, so it's giving you a velocity. So it says here, suppose the speed of the atom at 25 has been measured to within 1%, so meaning 1% of 350. That's essentially telling you the uncertainty in the velocity, a percentage of 350. So 1% of 350 is 3.5. So they're telling you that delta V is 3.5 meters per second. Okay. That's the answer. Calculate the smallest possible length of box which the atom can be known with certainty. So in other words, calculate what delta X would be for the atom, given that value of delta V. Okay. So this is not for an electron, this is for the actual atom. And then there's some details here. Write your answer as a multiple of the radius. The radius is 38 picometers. And for example, if the smallest box the atom could be in turns out to be 42 times the radius of the atom, you would enter 42 R neon as your answer, 42 times the radius. Okay? So let's take a look at this. So in order to do it, we need to know the mass of the atom. So we need to know what the mass is. 1% of 350 is 3.5 meters per second, so we know delta V. These are all constants. So really, we're just trying to find out what delta X is. Okay, so physically, here's what's happening. What they're saying is this neon atom, so I'll write it as a little atom here, is moving. It's moving at 350 meters per second. By the way, that's around 800 miles an hour, 800 to 900 miles an hour. And the uncertainty is 1% of that. So 1 over 100 times 350. That's what 1% means, 1 over 100. So that would be 3.5 meters per second. So there's your delta V. It's moving that fast, and we have that uncertainty. So the question is, if we measure it to within 1%, how big is a box that this atom is going to be in? In other words, how big is delta X? Now, it could be that when you do this problem, delta X is really small. It could be tiny. Maybe it's like right here. You know, maybe it's actually the size of the atom. So maybe we can tell that, oh yeah, it's right here. We know where that atom is. But maybe delta X is bigger. Maybe it's like this big right here. We don't know. So we do the calculation. Okay. So if you're trying to find delta X, you can just take this equation and what's the word for it? You know, derive it, right? Manipulate it, right? I'm trying to find what the word is. I think manipulate is what I'm trying to say. Okay, so in terms of the calculation, it's just easiest if you just write equal, because it says the minimum would be equal. So 6.626, I think yesterday when I did the problems, I remember it was 6.62607, right? Times 10 to the minus 34 joules. That's what H is. And then divided by MG. Okay, so I'll put M here. And then we'll put V here. So V is 1% of 350, so that's 3.5. Okay, so that should be, the question is what's M? So we have to be careful, it's a neon atom. So neon, it has a molar mass of 20.18 grams per mole. Okay, so that's just molar mass. But we want to know what the mass of one atom is, not a mole of them, but just one atom. So it's probably better to do it this way. Use the older atomic mass, 20.18 AMU. Because that's the mass of one atom. Right? This is the mass of 1 mole in grams, but this is the mass of 1 atom in AMU. But what's an AMU? 1 AMU is 1.661 times 10 to the minus 27 kilograms. And then, as you may have figured out already, this is in joules seconds, this is in meters per second, so we should probably do MKS. Let's put everything in the MKS system. So K meaning kilograms for mass. So we'll take our mass in AMU and then convert it to kilograms, and then we'll have a mass in the MKS system there. Okay. So 20.18 AMU, and then 1.661 times 10 to the minus 27 kilograms per AMU. Okay, so these are AMU. And so it's gonna be a nice small mass, right? So let's see what that works out. $20.18 times 1.661 times 10 to the minus 27, and you get 3.352 times 10 to the negative 26 kilograms. Okay, so there's our mass in kilograms. And then this is kg. Okay. So, let's see there. So,
What the convert kg to mass? Where it's
kilograms is a mass unit. So kilograms is the mass unit. It's also the mass unit that's in the joules, right? Because a joule is kilogram meter squared per second squared. So what happens is the kilograms up here are going to cancel with the kilograms down there.
because what we could convert it to grams.
Yeah, gram, because remember, grams per mole is what we typically use in chemistry, right? So this is CGS. But when you're doing these physics type problems, you want to use the MKS, so the kilogram is better. I'm just taking this delta X. What did I do here? I just want to see if I derived it properly. What we wanted to do was we wanted to find delta X. So this is H. I'm sorry, let me do this properly here. We're trying to find delta X. So what we want is we want to divide both sides by delta P. So delta X is H over 4 pi. But now we have to divide by delta P. Right? Does that make sense? But delta P is M delta V. So this becomes H over 4 pi times M times delta V. Okay? So what do I have here? I have M and I have delta V, but I don't have the 4 pi. I never put the 4 pi down there, right? That's what I did incorrectly. Delta X, we have to have our 4 pi down here. Okay. So H over 4 pi M delta V. That makes more sense there. Okay. Now, let's go through this because you asked that question about the units. It's not obvious how these units work out because this is in joules. But remember, a joule is a kilogram meter squared per second squared. So when you have joules times seconds, right? 1 joule second, you're going to have kilogram meter squared per second squared times seconds. Now, when we divide this by kilograms and we divide this by meters per second, these are units, right? So kilogram meters per second. So now we're going to divide this by kilogram meters per second. Now take a look at what happens in terms of differential analysis. One of these meters cancels with that one. This second cancels with one of those. And then this one here cancels with that one. And then kilograms cancel. And the only thing you're left with is meters. And since we're trying to find the uncertainty in the position, we would expect that to be in meters. Okay? So if we had left this in grams per mole, we would have grams per mole down here. We would have moles in our answer. We would have kilograms over grams. It wouldn't work out very well, right? So it's a good idea to have our. So we have our units. That's going to be in meters. Now the only issue is what's the answer? So let's see. Okay, so we're going to take this, divide it by this, divide it by this, divide it by 4, divide it by pi, and then that will give us our uncertainty in position. So let's see what that works out to. There's a lot of numbers, right? So 6.62607 times 10 to the negative 34. Then we're going to divide it by this mass in kilograms, 3.352 times 10 minus 26. And then we're going to divide it by 3.5. And then we're going to divide it by 4. And then we're going to divide it by pi. And it looks like, well, that's not right. That's not right. Divided by 5, divided by 4, divided by. So here's what 4.49 times 10 to the negative. Negative 10, so you get 2, 4, 6, 8, 10, yes. Okay, so there's your uncertain, sorry, so 4.49 times 10 to the minus 10 meters. Now, we figured out the uncertainty of the position, but now they want us to report it in a very specific way. It's a little confusing. What they say here is report it as a multiple of the radius. The radius is this value here, 38 picometers. So if we had come out with 38 picometers, that would be one radius. If we came out with 76 picometers, that would be 2 radii. Right? So we're doing it in multiples of radius. So what's the radius? 38 picometers. So radius is 38 picometers. Well, what's a picometer? Pico is 10 to the negative 12. So it's 38 times 10 to the negative 12 meters. So here's what you can do. Just take your position, your uncertainty, delta x, and just divide it by r. So take the value you got, 4.49 times 10 to the negative 10 meters, and divide that by r, 38 times 10 to the negative 12 meters. And that will give you multiples of the radius. Okay? So let's see what that comes out to. So divided by 38 times 10 to the negative 12, and you get 11.8. Did they say to round it to the nearest? Round it to the nearest. So that looks like it's 12. You see what we're essentially saying? We're saying that delta x over r is approximately 12, or another way of putting it is you multiply both sides by r. Delta x is equal to 12r. Right? It's 12 times the size of the radius. So if you divide the uncertainty, delta x, by the size of the radius, that'll give you multiples of the radius. Now look at that answer, it's 12 times the radius. In other words, if this is the size of the atom, 38 picometers, by measuring the velocity to 1%, 1% is like pretty good, but it's not like, some people do experiments at 0.001%. 1% is not that precise, really. If it was like a really close physics experiment. What they're saying is the uncertainty in the position is now 12 times the radius, right? 12 of these radii. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, 12R. That's a pretty big uncertainty, right? That is merely a result of the Heisenberg uncertainty principle, which says the better you measure the velocity, the worse you're going to know the position. It's not an issue of like how good our experiment was designed or how good the technology is. It's a fundamental limit of nature of how well we can know both of those things at the same time. So in this case, that's quite a bit of uncertainty in terms of our knowledge of where that atom is merely because we measured the velocity to 1% precision.
So I have a question.
Go ahead.
This uncertainty is just like a linear. It doesn't apply that also to.
Oh, that's a good question. So I guess the assumption would be that when they measure the velocity, so how do you measure the velocity of something? Well, one way you could do it is you could shoot light off of it like a laser. So let's assume that it was moving in this direction. So the uncertainty in the velocity is 1%. The uncertainty in the position would be just in this direction. So it's be one dimensional.
It's not.
Right, so it's just a one-dimensional problem. Absolutely.
Is there any reason they gave us temperature, or is it just like?
That's just put in there. So it's very often like when we give problems, you want to give the temperature so that people, in theory, could go back and reproduce it. So like if I said, look, you know, I measured the velocity at this 350 at this temperature, and then you did the experiment and you got 700 meters per second, you say, well, wait a minute. I had the same temperature, I got a different velocity. So did you do the experiment right? So then you would go back and you might publish an article and say, I don't believe these guys' results because I tried to duplicate their experiment and I got a different result. So that temperature is often put in there just so that people can reproduce the experiment. That happens a lot, actually. People will publish an article. People do this, they'll try to fake it. You know, because you can get promoted, you can get jobs based on the article's approach. So you publish an article and you make up the data. And so people are supposed to review it and say, hey, okay, all looks good, maybe it's published, right? But then someone will say, oh, that's a very interesting result. No one expected that. So then they'll try to reproduce it in their lab and they can't. So then they'll write an article and say, or not an article, they'll write a letter and say, I couldn't reproduce it. So then someone else will try, they couldn't reproduce it. So then people will start to investigate that person and put out the first article and say, how did you get this result? And eventually you can show, oh, that person didn't do that. It's called peer review. That's essentially how science works. All right, so that's the Heisenberg uncertainty principle. And you know, in chemistry, we generally only deal with the uncertainty in terms of position and velocity. But like I said, there are other uncertainties as well. For example, energy and time. So it turns out, just real quick, just as an aside, you can also show that there is a relationship between energy and time. And if you think about it this way, imagine I made delta T really, really small. If this is really, really small, this can't also be really, really small, right? They can't both be small. The smaller this one, the bigger this one is. So what that means is, even in space, I think a little space, like in outer space. And I say, okay, I'm going to make a vacuum in there. I'm going to suck out all of the air molecules and everything that's in there, so it's completely empty. There should be no energy in there, right? It's completely empty. But it turns out this relation seems to be true. So if you measure over a short period of time, there will actually be some energy in there. And that has been now investigated to show that there are actually particles that come into and out of existence in empty space. They're called virtual particles. So they appear, then they disappear. And they have to come and go because there has to be a certain amount of energy in space itself, meaning it's a vacuum. It's kind of cool stuff. So he came up with this idea. And that's an important aspect of quantum mechanics, because from our perspective, what it means is, if I want to say, okay, this electron's doing this, or this electron's doing that, you cannot really say that. We don't have knowledge of what the electron is doing, because to be able to answer that question, we would have to know where it is and how fast it's moving at all times. And what the Heisenberg uncertainty principle says is we cannot have that amount of information. We can only say what the probabilities are.
Well, I said,
Mhm.
tell like what, how big does that
How big is what?
How big does something have to be that this principle doesn't apply?
That's a good question. So what happens is it depends. So earlier problem that we looked at in the previous section of the de Broglie wavelength, it has to do with this value h. This value is really small. Right, so a lot of these equations that we see, for example, delta x, delta p, greater than h over 4 pi. Okay, you know, this is 4 times 3, that's 12. So essentially the main issue is this. So this is so small that this only becomes an issue when this times this is getting close to that value. So really, it's only going to happen when you're talking about atoms and electrons and protons, things that are that small. Because things that are, you know, velocity, you know, there's an upper limit, right? You can never go higher than that. You can never go lower than the speed of light. That's the fundamental limit. So that means there's a limit on how big that can be. The limit on how small it can be is 0, right? But then you say, well, what about mass? Well, this is where it really comes into. The mass is really what determines when this kicks into gear, when this becomes important. So, you know, it turns out for us, it's not an issue. Like our masses are so large that the uncertainty, the bigger this is, the smaller that becomes, right? So we are so big, our masses are so great that this is close to 0. There's no, you know, the uncertainty in our position is almost 0. Almost, right? It can't be 0, right? Because this times this has to be greater than this number. But this number is really small, 10 to the negative 34. So the uncertainty in our position is, it's not 0, but it's pretty close to 0.
How is it not zero?
Because if I say this, if I say x times y, it's got to be greater than 1.
But it's also equal.
Okay, greater than or equal. Neither of these can be 0, right? They can't be 0. If I put in 0, I get 0, it's got to be greater than or equal to 1, right? So for here, for this one, it's got to be greater than this. So it can be that small, it could be equal to it, but it can't be 0. Nothing in here can be 0 because it's got to be greater than or equal to this. But it can be pretty close to 0, right? Because that's a small number, that's pretty close to 0. Right? So for us, it's not an issue. For a planet, it's not an issue. Even for this, it's not an issue. Or even a fly. But for an atom, it becomes an issue.
How did it go?
What's that?
How did it go?
How did Heisenberg come up with this formula? He did an enormous amount of thinking about this problem, and he came up with essentially a thought experiment, which is this. How are you going to study something that's moving? So how do we know how fast something is moving in our everyday knowledge, and just like our experiences? How do you tell how fast something's moving? And so how do you measure it?
Meters per second.
What's that?
Meters per second.
Well, those are the units, but how do you actually tell how fast something's moving?
Point being how long.
Right, but, okay, so let's say it's right here, it's at point A.
This is what
How do you measure its position? How do you know where something is? Like, how do I know where you are? Good question. How do we know where things are? The way we tell where things are is from light. I use the light that's bouncing off of you and bouncing into my eye, and my brain is evolved enough to be able, through experience, right? A little baby can't do this. A little baby wouldn't be able to look at you and be able to make an estimate of where you are. But once they reach about 3 or 4 or 5 months old, they get the ability to say, oh, there's depth perception. I realize that something is smaller because it's further away. So I know through experience, I can't touch you from here, right? So the way I know, if you took out all the light in the room, I wouldn't be able to do that. I would have to use sound waves. I would say, you know, talk to me so I can tell how far you are. So really you're using waves. You use waves to tell where things are, and also to tell how fast they're moving. Because if you stood up and started walking toward me, the light would be changing, right? The light would reflect differently into my eyes, and I would be able to perceive that as motion. So when we tell where things are, it's through a collision. It's a collision of the photons that are striking the object and then bouncing off into the detector. So even if I want to tell how fast an atom is moving, what I have to do is I have to hit it with photons. Right? I have to hit it with these waves. And then those waves have to go into a detector. So let's say we're really sophisticated about this. Here's an atom. It's moving in this direction. I want to know how fast it's moving and where it is. I'm going to shine individual photons on it. And those photons are going to bounce off into the detector. And then I'm going to make a little gauge. And every time I get a little blip, that means a photon was detected. And so I can make a little sensor, right? That's how a radar detector works for a car, right? They shine a little light, the light bounces off of the car back into the detector, and then they use ranging, essentially radar, in order to figure out how fast you're moving, right? So here's the issue. Suppose I want to know where that atom is. What do I have to do? I have to use a photon, but here's what happens. Remember, photons have wavelengths, right? If the wavelength is really long, then the resolution of your position is limited by the wavelength. That's an issue for microscopy. If you want to look at something smaller than a cell, it's probably to use visible light, because visible light has a really long wavelength, so it's good at seeing cells, but you can't really see the fine molecules that are inside the cell, because the wavelength is too long. The wavelength determines how small you can see things. So you say, okay, well, that's not a problem because we have the electromagnetic spectrum. Let's make the wavelength shorter. In fact, let's be all fancy about it and use X-rays, because X-rays have really short wavelengths, shorter than the size of an atom. So we'll use those photons, and that'll allow me to tell where this atom is really well. So that's what you use X-rays. So now your delta X is going to be really small, right? Does that make sense? The shorter the wavelength, the better you can tell where this thing is, because when it interacts and bounces off, the shorter the wavelength, the better your resolution is. But there's a problem with that. Heisenberg saw it. The problem is E equals hc over lambda. The shorter this gets, the more energy the photon has. Now, when this photon collides, because it's got to bounce off, when it collides with that atom, the more energy it has, the more momentum it has, the more ability it has to move the atom. So this atom is moving this direction. When I use that X-ray, the X-ray is going to transfer some of that energy to the atom, and it's going to move over here. So now what have I done? I've changed its velocity. I've changed its position and I've changed its velocity. So he realized through that thought experiment that the better you know the position of something at the atomic level, that requires more energy. The more energy you have, the greater the velocity and uncertainty. So that's how we figured it out.
But technically, you don't have a certain position velocity, you just have a little.
Say that again.
Technically, you don't have a certain position and a certain velocity.
Oh, that's a very key question. So that gets into this issue of observation. If you don't observe it, what does it have? And it turns out that gets kind of spooky with these very interesting stuff. It turns out that the act of observing something changes it.
So really, there's no uncertainty, it's just about measuring it, yeah?
It appears as though at the atomic level, these kind of limits of measurement reflect something deeper in terms of what something actually is. So for example, if you have two states, you can do this experiment where you send in a wave. So let's say we have an electron here. This is your electron. If we send in this wave, if you put in enough energy, you can actually make the electron exist in this state. There's not enough energy to get it up here, so it kind of exists in both states. So that means the electron kind of splits into two. So it gets kind of weird at that level, because things start to behave differently at that level than we're used to. And so when we, people, that's what Einstein was like. He's like, wait a minute, like, It's doing something, right? If we just aren't smart enough to ask the right question, what is it actually doing? It appears as though the answer is it's doing something very different from what we expected. Okay, so what I want to do at this point is I want to talk a little bit about these quantum numbers. So let me back up just a little bit. And what I said earlier was that you have the nucleus. So here's our model. The nucleus is this little central particle. Nucleus is tiny, it's really, really small. And then what we said was that the electron is a wave around the nucleus, but that the actual wave itself isn't that useful for us. It's more useful to talk about probabilities. So we said that there's this thing called the orbital, right? So we said there's a space around the nucleus, which is this wave squared. And we call that orbital. And the orbital is really a probability distribution. It's the probability of the electron around the nucleus. Okay, so graphically it looks something like this. Large probability gets smaller. So this is distance from the nucleus. And then this is probability. Okay, so this is called an orbital. It turns out that if you start going through the mathematics of the atom, you can have more than one orbital. There's multiple orbitals. And these orbitals have certain properties. And these properties are a little different than what we're used to dealing with when we talk about rockets or baseballs or, classical physics problems. So the properties, the one is the energy. And the energy is, it's related to the distance from the nucleus. Which kind of makes sense, right? Because you think about it, an electron is attracted to a proton through electricity, electrical attraction. So the further away it is from the nucleus, the different energy it's going to have. Okay, so the first thing we can measure about an orbital is its energy. The second thing we can measure is the sort of what we might call shape. It's the shape. So this, if you take a look at this, this has a particular shape. It's a sphere, right? That's a spherical shape. The third is what we call the direction. Now, a sphere doesn't have much of a direction, right? A sphere is spherically symmetric. It has the same shape no matter what way you look at it. But it turns out there's other orbitals that have different shapes that can have directions. Okay? So these are three things we can measure about an orbital. And it turns out that each of these things we can measure about an orbital have what we call quantum numbers. So what I'm going to do is I'm going to write next to these quantum numbers. Now the first one you already know about, because it turns out Bohr's model was actually on to something. Energies are quantized. So the first quantum number for energy is called n, and it can have different values. 1, 2, 3, 4, 5, 6, 7. As far as you want to go, up to the counting numbers. Okay? So just like I would say in classical physics, I can know the x direction, I can know the y direction, and I can know the z direction. In quantum mechanics, you can know these three values. So the first one is energy, and that's given by n. The second one is called shape, and that's given by L. And it can take on values 0, 1, 2, 3, 4 all the way up to, but the limit is not necessarily infinity, the limit is n minus 1. So the value of L is actually limited by the value of n. So let's say that n is 5. The highest L could be is 5 minus 1, which is 4. So it could be 0, 1, 2, 3, 4. Has different possible values. These are called series, right? So there's not just one possible value, there can be more than one possible value. And then the third one is direction. Now direction is related to magnetism in terms of how it's measured. They first measured it using magnetic fields. So it's called M sub L. And it can take on 0 or positive or negative values. So I'm going to put plus or minus. It could be positive 2 or negative 2. All the way up to plus or minus L. So let's say L is 4. That means M sub L could be 0, or plus or minus 1, or plus or minus 2, or plus or minus 3, or plus or minus 4. So the upper and lower limits of M sub L are given by L. Okay. So what are some of the shapes? Let me talk a little bit about the shapes. Actually, before I do the shapes, let's do the NL. So let's talk about one energy. So if n is equal to 1, then you get essentially a shape that looks like this. So the nucleus is at the center, and the orbital is a little sphere. Okay. It's a sphere. So the electron is somewhere in that sphere. If n is equal to 2, then it's bigger. This is the bigger shape, a bigger sphere. Then it's bigger. The larger the value of n, the greater its size. If n is equal to 3, I think this gets even bigger. So you can have multiple orbitals, you can have different orbitals. And they just differ by the size. I'm exaggerating. It's not necessarily that scale that way, but essentially it's that. So that's the medium. Notice you can't have an n equals 0. Now let's talk about the shape. It turns out there are several shapes of these waves. So the first is the one we just talked about, the spherical. So if L is equal to 0, it's spherical. And here's the nucleus. Now what happens if L equals 1? If L equals 1, then the shape changes. It now becomes like a dumbbell. It has 2 what are called lobes. So here's the nucleus at the center, and these are called lobes. So you can have a sphere, or you can have these 2 lobes. And this is all one vibration. So it's kind of weird, but you think about it sort of like this. Here's the nucleus. The electron is above and below the nucleus, vibrating in and out. It's a wave that vibrates. And then if L is equal to 2, then you get 4 lobes. Kind of like this. Now it's even crazier, right? There's the nucleus at the center, and now you've got 4 lobes. And so it's like 4 different vibrations, 4 different parts of the same wave. We're not used to these kinds of waves. We don't generally see them, but it turns out electromagnetism, electrons, they have these particular types of waves. These are 3-dimensional as well. And then you have to L equals 3, the waves get even more complicated. They now have 6 lobes. So it's getting kind of hard for me to draw them, but there's like 3, 4, 5, and 6. There's the nucleus at the center. Nucleus, nucleus, nucleus. Okay. So this one has 6 lobes. This one has 4. Okay. So these are different shapes that we have. Now what about the direction? So it turns out if L is equal to 0, there's only one direction possible because a sphere cannot be rotated and look differently. Any way you rotate a sphere, it looks the same. Right? Think of it like a ball. If you rotate a ball, it doesn't change its appearance any way that you rotate it. But if you have lobes and you rotate it, they look different. You can kind of see they're changing their perspective when you take a look at them. So once you get up to L equals 1 or 2 or 3, you can have directions. Okay? And that's given by this M sub L. So what this says is, if L is equal to 0, M sub L can only go up to plus or minus 0. So it's only going to have one direction. And that's your sphere, one direction. But if L is equal to 1, now M sub L can be 0 or plus or minus 1. So it's got 3 possible directions. 1, 2, 3. If L is equal to 2, now M sub L can go from 0 to plus or minus 1 to plus or minus 2. That's 5 different directions. So what that means is for M sub L, the direction, when L is equal to 0, you only have one, just one direction, it's just a sphere. But if L is equal to 1, you can have 3. So you can have one that looks like this, or one that looks like this, or one that looks like this. 3 different directions. So I'll just write 1 for this one is a 3. Okay? It's essentially like this, or like that, or like that. So these are 3 different orbitals. Each one of these different ones is a different orbital. And then when you get up to L equals 2, you can have 5. So I'm not going to show them because I can't really draw them with any proper way. But essentially they rotate into different directions. So each of these ones have a different direction. So 5. And then this one can have 7. Why did I get 7? Because if L is equal to 3, you can go 0 plus or minus 1, plus or minus 2, plus or minus 3. So that's a total of 7 possibilities. So those are all different. So you get a lot of them, right? You can have N equals 1, which is this orbital. Now you go up to N equals 2, you can have this orbital, but then you can have these different shapes and you can have these different directions. It starts getting to be a lot of different orbitals. So let's take a look at see if we can talk about this. The principal quantum number is M, and the angular momentum quantum number is L. They're using a different, they're using a straight L like this. So now notice this over here. These are called subshell notation. Really, really simple. Subshell notation, what they do is they take the value of M and they put it in the front. So 4F would be N equals 4. So all you gotta do is say, hey, it's 4F, that means that N is equal to 4. And then you have a letter, and I haven't talked about the letters. Where do these letters come from? That's pretty simple. The letters are related to L. So this is subshell notation. So you put the value of N first, and then you put the value of L. And here's the angular momentum notation. If L is 0, we call that an S. If L is 1, we call it P. If L is 2, we call it D. And if L is 3, we call it F. So just memorize that right there. Okay. So for example, if I say 4F, what I'm saying is the value of N is 4, and the value of L is an F. F is 3. So that really means that L equals 3. That's essentially the notation. This will make more sense when we start doing problems. But this is sort of introducing it. So if you see 4F, that means L equals Now, I could ask one more question, which is, I could ask, how many directions can we have? And what you would do is you would say L is equal to 3. That means M sub L could be 0, plus or minus 1, plus or minus 2, plus or minus 3, and you'd have 7 possible directions. Let's try this again. What do you think about this one? What would be these two values for 7S?
First one, 7.
What's that?
The first one, 7.
Yeah, N would be 7. The principal quantum number, the energy, would be a 7. Now, what about the angular momentum quantum number?
0.
Yep, it's an S. So if it's an S, that means L is equal to 0.
Okay.
Hmm?
There you wrote L equal L n minus 1. Does that mean it has to be 1 less than n, or it just has to be less than n?
It means the highest value that can be is n minus 1. So it can be lower than that, but the highest it can be. So what that does is it puts a limit. It means that L can never be as big as n. So if I have 7, if n is equal to 7, L can't be 7. It could be 6, or 5, or 4, or 3, or 2, or 1, or 0, but it can never be as high as n. Let's try the third one. How about 6p? What would n be for 6p? 6, right? What does p mean? What does that tell us? P is 1, so that means L is equal to 1. So we would say the angular momentum number for that one, for the 6p, is L is equal to 1. Thank you, Mike, for bringing me the papers.
Yes, sir.
I appreciate it, thank you. How about the last one? 2p. Yeah, 2 and 1, right? N is equal to 2, and then p means that L is equal to 1. Okay, now from that we can get shapes, because the shapes are given by L. When L is equal to 0, it's a sphere. When L is equal to 1, it's a P. And when L is equal to 3, it's this one over here, the F, right? It has a lot of lobes. So we could draw these. So if we drew the 4F, here's what you do. You say, well, first of all, it's 4. So that means N is pretty large, right? N is not 1, 2, or 3, it's 4. So it's pretty big. And then F means it has 6 lobes. So it'd probably be something like this. A big orbital with 6 lobes. Okay, so that one if there's an electron in this orbit, it's vibrating in and out, 3-dimensional, these are 3-dimensional, right? It's vibrating in and out with these 6 lobes. What about the second one? The second one is 7S. So S is the sphere, right? When you're talking about L equals 0, that's an S. So it's just a sphere. But it's N is 7. That's a pretty big number, 7. So 7S is probably, a sphere, but very large. Right? The bigger they get, the higher the value of N. So 7. So it's just a very simple vibration, but it's pretty large. Then you have 6p. Well, 6p is a pretty big value. Then they're giving some very big values there. 6 is pretty big, right? So it's a big one, but it's a p, which means that L is equal to 1, which means it has 2 lobes. So it would be like big with 2 lobes. Okay. And then the last one, that one's a little more modest, right? 2p. So now N is a lot smaller, N is only 2, it's a P, which means L equals 1, so it's going to be 2 lobes. So this will be smaller. These are all relative. I'm exaggerating the sizes. These are things you can calculate, people calculate them using supercomputers, but that's essentially the general idea. What happens is, the bigger the value of N, more energy, right? So 6p, 7s, those have big values, then they have a lot of energy, they're very big vibrations. The smaller one, like 2, that's gonna have less energy and it's gonna be a smaller orbital. The P and the F and S, that's telling you the shape. So there's 4 shapes, right? And then you got these different values of energy. And like I said, this makes much more sense when we start talking about electron configurations. Then you get these sort of like little logic questions. So this one says, what is the smallest possible value of the principal quantum number for n, because principal quantum number is n, so it's kind of telling me that, for a d electron. So let me just kind of erase all this here. So remember, S, P, D, and F, that's telling you that L is equal to 0, 1, 2, 3. And that's called the angular momentum quantum number. These things have big names. Okay. That's really telling you the shape though. So for us, for most chemists, they just immediately think of shape. So if I say, hey, it's an S, that's a sphere. If it's a P, 2 lobes. If it's a D, 4 lobes. If it's an F, 6 lobes. That's the way we kind of imagine it. Okay? But it turns out those numbers are important. So this is really getting into numbers. And so let me write these again. 1, 2, 3, 4, 5, all the way up to infinity. L, 0, 1, 2, 3, 4, 5, all the way up to n minus 1. Okay? And then m sub L, which I don't think we need for this one, 0, plus or minus 1, plus or minus 2, plus or minus 3, all the way up to plus or minus L. That's nice. So this one's getting at the relationship between n and L. And here's how you can approach it. It's telling you it's D, right? See, it says a D electron. D means it's an orbital is a D. So if it's a D, that means L equals 2. Okay, so for this particular problem, you're saying L is 2. So the question is, what's the smallest value of n that you can have if L is 2? Yeah, what you do is you say, wait a minute. The highest L can go is n minus 1, right? So the highest that L can be, if L is 2, that means the it corresponds to 3 minus 1. 3 minus 1 is what gives you 2. So that means that n has to be at least a 3. Now it could be more, right? Because if I say 5 minus 1, that's a 4. L just has to be less than n. So it can never be as large as n. So that means that L is equal to 2, n has got to be at least 3, but it could be larger. So the minimum that n could be is a 3. So you just gotta add 1 to your L, and that'll tell you what the minimum value of n could be. Let's try one more. This one says, list all the possible values of the angular momentum quantum number. So that's this. That's the angular momentum quantum number. By the way, this one's called the magnetic quantum number. And then this one's called the principal. So it says, list all the possible values of the angular momentum quantum number L. So that's giving you a hint. For the atomic electron with a principal quantum number of 5. So if n is equal to 5. So I like this one because it goes through the idea. So what they're saying is n equals 5. And what can L do? So be careful. L is limited by N, right? So if N is 5, that means L could be 0 or 1 or 2 or 3, all the way up to N minus 1. Right, so what you do is you just say 0 all the way up to N minus 1. N minus 1 is 4. So that means it's 0, 1, 2, 3, or 4. So there's actually 5 different possibilities for that. Okay, and this would be S, P, D, F. I didn't actually tell you what happens when L gets up to 4. We don't usually do it in chemistry, but they put it in here. It's called a G. But you're not going to be asked. Okay, so this is very abstract material. It's all kind of dealing with these numbers and these names, and it may not make much sense to you right now, like why are we doing this? But what we're going to find, and we'll start working on this for the rest of the week, is that it turns out these numbers can tell us the positions of the electrons in the atom, where they're going into the atom. And at the end of this chapter, we will bring it back into the chemistry, and we'll bring it back into the periodic table, and we can describe the properties of these elements even based on these numbers. Okay? All right.